Hi everyone, I'm Darren, and my partner Kameron and I are going to go over our uniaxial characterization of porcine lung tissue and its therapeutic significance. Now, for our project overview, our goal was to investigate the impact of data volume and sample specificity on results of biomechanical modeling. We compared the outcomes of model trained on partial data sets and also explored how individualized models for each lung sample differ from an average model. The data collection, we use an open source lung sample data set of 5 different porcine lungs, and they cut the lung tissue and put it under a uniaxial tension and an instrument machine with a 50 Newton load cell. And the sample data is on the right. Now, we had to do some brief modifications to the data by our strain by adding one so that we could properly implement it into our neural network, where we used the first two invariants as we assumed that it was isotropic and incompressible as stated by the paper. With 2 hidden layers and 24 weights, we implemented the Mooney-Rivlin and Demarest model for our physics and looked at the PL stress. Now, the evaluation methods included the loss function in R squared to help evaluate our data outcomes.
And so basically the first thing we did was we wanted to start looking at whether the regularization L1 versus L2 and the penalty had any effect on it. So we ran the model for each run and the average of all those runs, and these were the results we got for both the L1 and L2. And what we found was that it really didn't matter what the regularization we used was and what the penalty was. We got pretty good performance in terms of R squared value across all models. So we were wondering what happens if we pare down the data set to just 20 evenly spaced data points. And here's our models once again for L1 and L2, and much of the same story in terms of R squared value. So we learned that that didn't really matter that much in terms of providing a good model. And so then looking at mapping all the runs onto the average model, these are the 100 data point models. And so we see that run 4 has pretty good performance, while runs 2, 3, and 5 are so-so, and then run 1 is not well modeled by the average model. That's in the L1 case, but the same is true for L2. And then even when we look at the 20 data point models, it's a lot of the same story. And so overall, just looking holistically at what the average model looks like, we see that we have a lot of activated functions in the invariant. So those are the warm colors, and then a single function activated in the second invariant.
Now, if you want to look at the limitations of our data and the implications of our project, here is a stress strain of all of the porcine lungs, including the averaged run in red. As you can see, there is quite a variation between all the stress strain curves, and the run 4 is closest to our average model, hence its performance relative to all of the other lung samples. And in general, lung tissue is heterogeneous, and so there are a lot of variations when you're using the instron to get your stress strain curves, and so that's going to impact the performance of your neural networks. And so moving forward with implications, down the line, we hope to eventually use individualized biomechanical models to potentially inform more targeted therapeutic interventions and get a better model of the material itself. And this project also provided insight into the computational efficiency, as we could parse down our data set and still get relatively well-performing neural network models.